In statistical analysis, a hypothesis is a conjecture about the value of a true population parameter. When you test for hypotheses, you actually need two competing hypotheses. A null hypothesis, denoted by H0 or H0, and an alternative hypothesis, which we denote by H1 or HA. We test the hypothesis by evaluating it against experimental evidence, against observations. We reject the null hypothesis if the evidence against it is strong, and we fail to reject it if the evidence against it is insufficient. In the first example, in the previous slides, when we had only tossed the coin 10 times, we failed to reject the hypothesis that the coin was fair. The evidence against that was insufficient. In the second case, when we tossed the coin 100 times, we ended up rejecting the hypothesis that the coin was fair, the null hypothesis, because the evidence against that was strong. When the evidence against the null hypothesis is strong enough, and we'll talk about what that means shortly, then we say that we reject the null hypothesis in favor of the alternative. In that case, the evidence against the null hypothesis in favor of the alternative is significant. If the evidence against the null hypothesis is not strong enough, then we fail to reject the null hypothesis, and we'd say then that the evidence against H null was non-significant. It is very important for you to remember that when we fail to reject the null hypothesis, that does not mean the same thing as us accepting the null hypothesis. Right? All you're saying is that you did not have enough evidence to reject the null hypothesis. Whatever hypotheses you will be testing for, they should be formulated prior to the start of the experiment or the study or the data collection process. Right? You run the experiment, you collect the data, you look for observations to evaluate the evidence against the null hypothesis. If you don't do that, then you run the risk of data snooping, right? Using the data to tell you what it is that you should look for, then testing for that thing in the data. Surprise, you're going to find that it's there. You can't do that. This isn't something that you can do in statistical analysis. You have to formulate H1 before you look at the data. From a scientific perspective, hypotheses are often expressed in terms of whether there's an effect in the data or not. So if that's the case, you're looking for a null hypothesis that would look like this one here. H null, there is no effect. Against the alternative hypothesis, H1, there is an effect. One of the major components of hypothesis testing is the idea that we have some way of measuring the types of errors that can be committed when you test for your null hypothesis against the alternative. It could be that on the basis of the evidence you reject the null hypothesis, or that you fail to reject the null hypothesis. These are the only two options that are available to you here. If you fail to reject the hypothesis, well, there was two other options. Either in reality the null hypothesis was true, in which case you've committed no error by failing to reject it, but it's conceivable that the null hypothesis was in fact false. And then when you fail to reject it, you commit what we call a type 2 error. If you had decided to reject the null hypothesis, if the evidence was strongly against the null hypothesis, then there's two possibilities again. It could be that in reality the null hypothesis was indeed false, in which case you've committed no error. But it could have been that the null hypothesis is true and then you falsely rejected it. If you reject H null when H null is true, you're committing a type 1 error. The first one I described was the type 2 error. If you conclude that a drug treatment is useful for treating a specific disease, but in reality you were wrong, that's not the case, then you've committed an error of type 1. If you cannot conclude that a drug treatment is useful for treating a particular disease, but in fact it was effective, then you've committed an error of type 2. And then there's a fundamental question about these types of errors. What type of error is the worst? Well, it actually depends on the situation. There are times when an error of type 1 would be worse than an error of type 2. In particular, if you conclude that the drug treatment is useful, but it wasn't useful, in fact, it was harmful, then prescribing the drug to somebody who has the disease, well, you've committed harm. If it's just a placebo, you might just say, oh, well, there's no harm. Presumably there's no harm to their actual health, but there might be harm to their mental health, thinking that they're actually following an effective treatment when in reality it does nothing. The probability of committing an error of type 1, we usually denote it by alpha. And here the choice of notation is not arbitrary. We're using this alpha so that it fits with our notion of confidence level. Small values of alpha allow you to build 1 minus alpha times 100% confidence intervals. That's the probability of rejecting the null hypothesis when you assume that the null hypothesis is in fact true. And it's a measure of how good your test actually is. How well the data that you have is attuned to your ability to test hypotheses. The probability of committing a type 2 error is usually denoted by beta. It is the probability that you would fail to reject the null hypothesis when the null hypothesis was in fact false. And the power of a test, that's the probability of correctly rejecting H null. The probability that you would reject H null when H null was in fact false. The fact that we have a named concept for this probability here seems to indicate that errors of type 2 are usually seen as worse than errors of type 1. That's not always going to be the case, but that's often going to be the case. What are the values of alpha, beta, and power that people usually look for in their tests? Well, the convention is to use an alpha of 5%, a significance level of 5%, a confidence level of 5%. But that's just a convention. There's cases where you might be able to get by with 10%, 20%. Sometimes you might need 1% or 0.1%. Values of beta often are going to be 20%, and then values for the power then would be 80%. You can think of this as the confidence being a quarter as large as the probability of committing type 2 error, which is yet again a quarter as large as the power of the test.